Hey, welcome to Zig for the Uninitiated. My name's Tyler. Today I want to talk about some comptime reflection and some new tools that you can use to help working with it. So comptime reflection is perhaps one of the most useful, in my opinion, uses of comp time in Zig or compile time. It allows us to do things that wouldn't be feasible at runtime. And to give you an example of this, I've implemented a portion of the size of built-in in Zig using userland code. And I want to walk through it to show what that means and how we use compile time programming to use that. So, in particular, compile time reflection. So the first thing that we do here is userland function. The userland size of takes in a type t, which is the same as the regular built-in function at size of takes in a comp time known type. We take in that type and we get the information of it. So this built-in at type info provides us the reflection, the kind of type information we're allowed to use when we're doing reflection. And it generates actually a userland type called type. So if we look at what it generates, it's a union of several different types. And these types are type, void, bool, no return, int, float, pointer, array, struct, comp time float, comp time int. You have all these different types you can loop over, or not loop over, that you can access at compile time, and you can start getting information about them. So what we do for our userland structure, obviously we're going to make some result value. So we'll first switch on the struct type here, and we'll capture what we get there. If we look at that, we see struct is this. We go to the type, we can see what values are available on that struct. We can see its layout. You also see that there's a backing integer, though that is only valid if you're using the packed layout, which again, we'll need to talk about a different time. And then you get a list of fields and declarations. And this fields value is what's going to be really important for us, because when we are calculating the size of a struct, we really care about what the size of each field in that struct is. Now that we've switched on the struct tag, we can start calculating the size of that struct. First thing that we're going to do, ignoring this alignment part, is loop over all the fields in the struct and then calculate their size of using the same userland size function. And how we do that is by accessing that fields field of the struct type struct. It's kind of meta, which is why it's called meta programming. And we can capture every field. So if we look at what the fields are on the struct field, we can see what kind of data we get from there. We can get the name of the field and its type, its default value, if there is one, and then just a true or false if that field is a comp time field, which is not that the value is comp time, but that the field is declared to be comp time. So it's a little nuance. We'll have to get into that maybe another video. And then it's alignment. And so the things that are going to be super important for us here in calculating the size of the struct are the alignment and the type. So the first thing we're going to do is get the type of the function, or not the function, get the type of the field. And then we use the same userland size of function to get its size and add it to our result. We then calculate the alignment, or we get the alignment. And what we have to do is find the maximum alignment, because the alignment of a struct is always the same as the largest alignment of any of its members. And so we find the alignment of the field and we store that. By default, the alignment is going to be 1 byte. We then do some calculations here to bring our struct size into alignment. Basically, we find out how far off it is from being aligned, and then we just add that in. And if it is exactly aligned, then we don't add anything. That is the main part of what we're doing here. Elsewise, we've implemented it for bool. So if there's a bool type, if this is given a bool, we just say the result should be 1. We get an integer type where we calculate the size of an integer based on how many bits it takes. Essentially, we divide it by 8 and then round up to 1 if we need to. I've left the rest to be done later. For the purposes of this example, we're only going to deal with ints, bools, and structs. So then we have this struct. The struct has a bool and a U64, and we can then see a test where we just expect that the size of this struct A should equal the output of our function. And if I run this code here, we do zig test inline loop, we'll see that all the tests have passed. Now, if I got rid of this inline, and this is something I wanted to show, is this is what would happen if we didn't have an inline for. We'd get this error here. An error telling us that the struct field must be comp time known, but that the value, the index value, is runtime known. And so when you're looping over a field, you're kind of using runtime known indexes to loop over it. But because those indexes are runtime known, we can't then use them to go back at comp time because they're happening at separate times. And this is a compile error. And so this is why in this case, we must use an inline for. Now, there are cases where you might want to use an inline for where you're not dealing with comp time data. However, the standard documentation insists that you should use inline for only with comp time documentation or in cases that you have benchmarks that show you that it is faster to unroll the loop by hand. And the reason for that is because it forces the code to be unrolled. Whereas if you let the compiler do it, it can decide if it thinks that it would be more performant to be unrolled. So this is it for my little video here about the inline for loop. Next time, I think we'll probably talk about the comp time keyword. And then maybe after that, we can talk about the inline switch. I apologize, it's been a while since I've made a video. I've had a hard time coming up with the next videos. But I think I've got some ideas now about what we want to do, in particular with discussions about compile time. If you got any questions, please leave them down in the comments or head over to zigit.dev where there's a lot of discussion happening. It's a great place if you're learning about Zig to ask questions and get really good feedback from people who program in Zig daily, who use Zig at their work, or are even core developers on the Zig programming language. Anyways, see you next time. Happy coding.